Hi, pre-calculus friends. Hello, pre-calculus friends. We're in chapter 3.7, and we're looking at graphs of rational functions. Let's take a look at some vocabulary today. So our vocabulary includes the following terms: rational function, asymptotes, vertical asymptote, horizontal asymptote, and slant asymptote. So really the main feature of today's lesson is going to be about this concept of rational functions. What are rational functions? Rational functions, in a short way of thinking about it, will be like a ratio of two functions in a sense. So f of x is equal to some p of x over g of x. Now, what kind of functions are these? Usually these functions are kind of more polynomial functions. You remember polynomials. You might have a linear polynomial where the x is the main thing, or a quadratic polynomial where x squared is the main doer of the action. So it's going to, here linear is going to give you a line. This guy will give you a parabola. X cubed will give you some, curve, some cubic curve, and x to the fourth, and so forth and so on. So usually you'll have one of these types, or both, or two of these types of things as your p of x or g of x, in order to give this ratio of functions. So that's what's happening, and that's what we're going to talk about. What is an asymptote? An asymptote is a place on the graph that you're going to get closer and closer to without actually touching. Now, that seems like, okay, whatever. We've seen those. All right. So sometimes you'll have, and we'll just talk about all asymptotes real quick. Sometimes you'll have a vertical asymptote, and I'll draw my asymptotes in red here, or reddish. So let's say you have an asymptote at, let's say, the value x equals 2. That means your graph can be doing all kinds of stuff on either side. So we can have like some kind of a movement here where it does that, but it's never going to actually touch that. It's never going to cross that space. So it might get closer and closer to it. And then on the other side, you might have it being asymptotic there as well, okay? And something like this happening. So an asymptote, a vertical asymptote, is a vertical place, an x value, where the graph or the function will never actually have a value. It's not defined there. And in addition to it not being defined there, you're also, excuse me, you're also not going to actually be able to cross. You're going to kind of continue to approach this vertical line, but you won't actually cross it. All right. So this is different than just having like a graph with a hole in it. Like you can have a graph with a hole in it at 2. That's not a hole, but you guys get what I'm getting. So a hole in it at 2. This is not an asymptote. An asymptote is literally a place. It's almost like a force field. If I'll get into my science fiction thinking, it's almost like a force field where you're getting closer and closer to it, but you can never actually pass through it. So that's a vertical asymptote. A horizontal asymptote, maybe I'll do my horizontal asymptote in green. A horizontal asymptote is going to be a little bit different. So it's going to have that same feature, right, of getting closer and closer to a particular thing. But when you have a horizontal asymptote, what happens is that you can actually sometimes cross it. Sometimes, let's say this graph has a horizontal asymptote like there. You cross it, and then it'll kind of come back, and then eventually it'll be approaching that green line. Let me make that green line longer. It'll approach that green line, but it can never cross it. It'll never pass it. And so that is a hallmark of horizontal asymptotes, that sometimes you can cross it in the beginning, and that's not odd. Whereas vertical asymptotes, you're not crossing those bad boys, okay? So again, a horizontal asymptote is more about end behavior. So we think about horizontal asymptotes, particularly when we think about, okay, as x goes to infinity, what's happening with f of x? What is it approaching? And so remember before we talked about x goes to end behavior, as x goes to infinity, the function would generally go to negative infinity or positive infinity. And as x goes to negative infinity, we'd have a similar situation. Well, now when we have a vertical asymptote, we kind of have a bounding of our function, so that as x goes to positive or negative infinity, f of x might actually approach some number. It might be some value that f of x is approaching at at these times. So that's what we're looking for. And we're going to have a way of deciding or determining that just by looking at the rational function. Finally, so we got vertical asymptotes, but I didn't tell you this. Vertical asymptotes usually come from the denominator. So if there's something in the denominator that's going to make the denominator 0, for instance, if this function might be like x minus 3, then this 3, you can never put a positive 3 into this equation, right? You can put numbers close to 3. You can kind of sneak up on 3, as we did before when we were thinking about limits, or we were thinking about continuity, rather. We can sneak up on 3 by putting numbers closer and closer to 3, and they'd all have values in the function, but as soon as we got to 3, it wouldn't work. So what that would refer to is the vertical asymptote. So the vertical asymptote is usually going to be found by looking at the denominator of your rational function. Horizontal asymptote, a little bit more complicated. We'll talk about how to get there. And slant asymptote, similarly complicated in a sense. Not complicated, just requiring some rules, and an example will work better. But a slant asymptote is going to be exactly what it sounds like. And not every textbook talks about this, but a slant asymptote is like a linear equation line, right? Like a line that we would be used to graphing y equals mx plus b, that my rational function will never actually get to. So, or it could cross it and then it can kind of be like tangential. So you might have a situation like your graph does something like this, comes down, comes up, and then it's always kind of barred from crossing this red line. And so this is a slant asymptote. It's very similar to a horizontal asymptote, except you'll see when we talk about it. So that's asymptotes. Asymptotes are like these fields that you can't actually cross, or you can cross, but later on you'll not cross. So in this circumstance, you'll cross them. This circumstance, you never cross them. And rational functions are kind of like two polynomial functions being divided together. Let's get into some examples. Okay, so here we are. We're going to determine the asymptotes for this graph. So the first thing is we need to figure out if we have 3 different types of asymptotes like we talked about before. So vertical, horizontal, and slant. And as I indicated before, the way you're going to look for a vertical asymptote is to, first of all, just make sure that you factored out the numerator and the denominator. And the numerator and the denominator of this rational function is factored out. And what we're going to highlight or focus on is the denominator. So once you've factored out and you've canceled out anything that can be canceled out, because if you remember, when we cancel out things in the numerator and denominator, that's a hole in your function. That's an empty space. But when you have a factor that doesn't cancel out and that you can make 0, well, that's going to be a vertical asymptote. So what makes this 0? X equals 2 makes it 0. So the equation x equals 2 is the vertical asymptote. All right, so that's one thing we have. Horizontal asymptotes. Now, generally, you're not going to have a horizontal and a slant asymptote at the same time. So you kind of have to go through this in order to see if you have you'll have to check this out. So here it is. We have a couple of things that we're going to test for. First thing is we need to look at the degree of the numerator and the degree of the denominator. The degree is the highest order usually x variable that we have in the numerator. So this is degree 1 and this is degree 1. So if the degree of the numerator, and that's what I'm going to use for that, and the degree of the denominator are the 2 things that we're going to talk about it. So if the degree of the numerator and the degree of the denominator are equal, if they are the same, okay? When we have this situation, then I want you to know that the horizontal asymptote will be the ratio of the coefficients of the lead coefficients. Okay, so I figured I'd better tell you all the things right now. So here's what we need to know. We need to know that what the degree of the numerator and the degree of the denominator is. If they're equal, then we have a situation here where y is equal to the ratio of the coefficients, of the lead coefficients. That is the horizontal asymptote. What does that mean for our problem up here? Let me scooch up a little bit. So if you notice the ratio of the coefficients, this is 3, this is 1. 3 over 1 is the horizontal asymptote. So y equals 3, that horizontal line at y equals 3, that's the horizontal asymptote. We can think about this a little bit. Think about as x goes to, remember I talked about x goes into infinity is how you figure out the horizontal asymptote. As x goes to positive infinity and negative infinity, we kind of figure out what y is approaching or what f of x is approaching. Think about this real quick. If you put larger and larger numbers in here, big numbers, a billion, a trillion, whatever, this function is getting really close to 3. Like, this is kind of irrelevant, but relevant enough that it's not going to be at y equals 3, but it's getting really, really close to 3. Can you think about that? Even pause me just to say, what was you talking about? Think about what that means. As these numbers get particularly small, as we move closer and closer to negative infinity, right? As we move closer and closer to negative infinity, these numbers, let's make x go to negative infinity, these numbers is getting the thing that matters is really just this ratio, 3 to 1, 3 to 1, 3 to 1, 3 to 1. This is kind of irrelevant, but relevant enough that it won't be that this function won't be uh, that the f of x value won't actually cross that line. It'll continue to approach it and get closer and closer, but it won't cross the y equals 3 line. Are you kind of with me? I hope you are, guys. All right. So let me get rid of all this and let's talk about some of these other situations, even though we have figured out that the horizontal asymptote for this particular problem is y equals 3. And I will highlight that just so we can keep it in the forefront of our mind. However, let's talk about these other circumstances. What if the denominator, the degree of the numerator was less than the degree of the denominator? So that would be a situation where we had like f of x is equal to x over x squared or something like that. What you're figuring out is, or you're thinking about, we could even plus 2x minus 1, all this stuff. What's really the heavy hitter in the numerator is this x term, and what's really the heavy hitter in the denominator is this x squared term. So as I get x closer and closer to either positive or negative infinity, right? As x goes closer and closer to positive or negative infinity, really it will think positive infinity and negative infinity as, at the top and bottom at the same time. But as x approaches that, we realize that this x at the top is so wimpy compared to this x at the bottom. So what does that mean? It means that as this gets closer and closer, this gets bigger and bigger, this is getting bigger faster. And the faster this gets bigger, the more this approaches 0. It's not going to get to 0, but it approaches 0. You know how when you have a little number at the top and little number at the top and a big number at the bottom, this number is really, really small the larger the number is in the denominator. Let me make sure my commas make sense. Yeah, so as this number at the top is small and this one's big at the bottom, this is approaching 0. This is so close to 0, it might as well be 0. 1/4 millionth of a thing is like 0. So that's kind of what we're thinking about. As these guys get closer and closer to infinity, as x approaches infinity, well, it's just going to be 0 because the bottom is outdoing the top. Whether we're talking about both x in the numerator and denominator going to negative infinity or positive infinity, it's the same idea. All right. It's the same idea. This might have interesting issues in terms of going to negative infinity, but this being positive, where the value goes. But we'll talk about that as well. So, and finally, the last concept I want to talk about in terms of asymptotes here is this idea of the numerator's degree being greater than the denominator's degree, then there is no horizontal asymptote. So these are the only two situations you're concerned with. And then I had like a little arrow pointing here. Then the question is, do we have a slant asymptote? Do we have a slant asymptote? And that's a situation, a slant asymptote. And this is the last I'm going to say. I know I'm killing this problem. Please be patient with me. But the slant asymptote is going to be a situation when the degree of the numerator minus 1 is equal to the degree of the denominator, meaning the degree of the numerator is just 1 more than the degree of the denominator. So if I had y equals, or f of x is equal to x squared plus 3x, blah, 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 over x plus 4, this would have a slant asymptote because the degree of the numerator is just 1 more than the degree of the denominator. If I throw a 3 here, that's not going to be the same thing. They really have to be exactly 1 degree away from each other. Are you with me? I hope you are, sweeties. Okay. All right, let me pause this and go on to another example. So in example 2, we're going to be talking about how this graph of the parent graph, this parent graph that we're kind of familiar with, hopefully, is one that you remember f of x is equal to 1 over x. And if you think about it, it's got some asymptotes that we need to think about. And it's got a vertical asymptote at 0. And it's got a horizontal asymptote at 1, at 0 as well, at y equals 0, my bad. So this graph does one of these things, these funky little kind of a hyperbola situation. Okay, well my graphing was not getting the job done. So I said, let me grab a little grid so you can see what it looks like. So this is what the parent graph looks like of f of x equals 1 over x. And you see that we have a vertical asymptote at x equals 0, which is not surprising because that's what will make the denominator 0. And if we think about the degree of the numerator and the degree of the denominator, we can see that the degree of the denominator is bigger, and therefore we know that y equals 0 is the horizontal asymptote, okay? So this is the vertical asymptote, this is the horizontal asymptote. And so now we kind of get an idea of what's happening with this graph. We're going to use this information to graph these other guys. So as I look at part A, g of x rather, is equal to x plus 5. What I want to recognize is that this is the difference between this original function. And how does this affect it? Well, we talked about this earlier, right? We said that we get the vertical asymptote by looking at the denominator. After we factor out the numerator and denominator, we figure out what's going to make the denominator 0. And what will make the denominator 0 is -5. So -5 will be the vertical asymptote. And so I'm going to just call this -5 here and recognize that we have a vertical asymptote here. We could also think about this in terms of the parent graph. Remember, x plus 5 means to shift everything back on the x-axis to 5, so a vertical shift. We can think about it that way in reference to the parent graph. And what's going to happen is we still have the horizontal asymptote right here, and then so our graph will do one of these numbers. Not actually cross that. So let's try it again. It'll do that, and then it'll do this. And so if we look at this next one, all right, does that kind of make sense? Let's look at this next one. So if we look at this next one, we see we have a similar situation. We don't have a shift necessarily, but we have like this whole thing being multiplied by, well, the x value being multiplied by 2. And we talked a little bit about what that does to the parent graph. When you multiply just the x term by a particular number, what you're going to do is make rapid the changes that happen across the horizontal axis. And in addition, we have this negative, and we know that negative gives us a reflection. So a couple of things are happening. We're going to have this whole thing happen faster. And in addition to it happening faster, we're going to have the entire graph to be flipped over the x-axis. So what we have here is like a zoomed in look at the f of x is equal to 1 over x function, right? And so we could see when x is 1, y, or f of x will be 1. When x is 1/2, y is going to be the reciprocal of that 2. And when x is 2, y is 1/2. So we have that, and we have the other occurrence that we would have in this third quadrant. All right, so now let's think what's happening with this 2 in the denominator. So what happened when x was 1 is going to be now the same thing that happens when x is 2 times 1. So when x is 1, remember, when x is 2, we're actually going to be down here. So everything's going to happen faster when we look at this graph. I'm not even looking at that negative right now. So in a way, it could be looked at as a vertical stretch, but we'll talk about that later. It's kind of a horizontal compression. So it's like everything happens much faster here. All right, so we're going to have kind of a squeezing of that function along the horizontal axis. And then the next thing that we're going to have is this vertical flip. And so the vertical flip would just be a flip over the x-axis. So we get h of x is equal to -1 over 2x. That's this darker blue function. Whereas this light blue function, I'm going to call it t of x, it was kind of an interim function where we were just looking at what happened with the 2, and then we saw that the negative gave us the final answer. Let's go ahead and graph another one. So if we go back and we consider this to be a generic of our parent graph, this 4 is going to multiply the entire function times 4. So we're going to be having a vertical stretch of 4. So things are going to happen faster that way. But then we're going to have a shift, a horizontal shift over to x minus 3, because we can see that x equals 3 is the vertical asymptote. So that's going to be 1, 2, 3 over here. Vertical asymptote there. The horizontal asymptote is the same. It's been the same in all of them because the degree of the numerator was always smaller than the degree of the denominator. And so we're going to have that y-axis horizontal asymptote situation, but we're going to have something more speedy coming down and doing that and doing the same thing here, kind of increasing much faster. In fact, increasing by an amount of 4. And finally, we've got this last guy here that looks complicated, but I think we can handle it. We've got a few things going on. First, we've got a drop of 4. So that means our horizontal asymptote is going to be dropping down by 4. I could talk about why this doesn't fit our horizontal asymptote discussion from earlier real quick, or I can show you real quick too. So here, if I'm saying that the horizontal asymptote is going to be a negative 4, but it's like, wait, this doesn't fit any of the rules. But watch what this is equal to. So what I did is I just made sure and wrote this 4 with the, I combined these two terms. So I had to give this 4 a denominator of x plus 2. And when I do that, we actually get the two polynomials, negative 4x minus 14 over x plus 4. And so according to our rules, since the degree of the numerator and the degree of the denominator are equal, the horizontal asymptote will be at negative 4. You see that? Like, because it's a ratio? All right. Just wanted you to see that. I'll get rid of that work. And we'll proceed with considering this graph. So I already know I have a horizontal asymptote at negative 4. So before, they were always at the y-axis, so I didn't have to draw this in, but I'm going to draw in this horizontal asymptote. And let's, at the same time, draw in the vertical asymptote. So you can see that there's a vertical asymptote right there at negative 2, because that's what will make the denominator 0, and that will be a problem. So I'm going to come back here at negative 2 on the x-axis, draw a vertical line, and that's what we have going on. So now, in a sense, we've got these boundaries that we can kind of think about our graph, and that's totally fine, but we also need to consider what's happening with this negative, and we need to consider how it relates to the parent graph. So what I know is that this negative is going to give me that flip. This 6 is going to give me a stretch by 6 vertically. And so I'm going to do a quick quick drawing of this graph like that. Actually, it's going to be stretched out even more. Swoop and swoop. But wait a minute, you guys know what I didn't do. I didn't take account for the flip. So I've got the shifts, everything, but this is like the standard graph, and the flip is going to be in a different direction. So let me go ahead and get that together. So there we have a flip over the, I was going to say over the x-axis, but you know, we have like a flip, a negative flip, kind of over the x-axis. That's changed here, and this is the graph. Ooh, that was long. All right, I'm going to pause this video here, and I'm going to give you guys time to kind of absorb this before we start a part 2. All right, take it easy.